This video will show how the standard algorithm for division is almost identical to the partial quotients method. So most adults learn to divide using the standard algorithm. So I'm going to walk through that method, which is how we all learned how to divide and how we were all taught to divide as adults. 5 goes into 8 one time, multiply by 5, subtract, I get 3. Then I bring down my 2. 5 goes into 32 6 times. 6 times 5 is 30. Subtract, I get 2. I'm bringing down my 6. 5 goes into 26. How many times? It goes in 5. 25. I subtract, I get 1. I bring down my 1. 5 goes into 11 twice, which is 10. And I have this remainder of 1. It seems very easy because that's what we learned, and it's a set of steps. However, this doesn't show students any understanding of what's really happening. So doing this exact problem side by side with the partial quotients, here's what's really going on when we're showing your child how to do partial quotients. So we're essentially doing the same thing, but we're showing students that this number here has a value of 8,000. And when we do it our standard way, we say, well, 5 can go into 8 how many times? Well, it goes in 1 time. This way is saying I have 8,000s and I want to put them in 5 groups. I can put 1 in each group. That's where this 1,000 comes from. If you look at the number you placed over here, or we placed over here, this 1 also has a value of 1,000. But when students are doing this method, and if they're only taught this method, it's not easy to see, or it's not easily explained or understood by them that this 1 is 1,000 until they finish the problem, which makes it difficult. If there's ever a 0 in the quotient, students don't understand what's happening. So the partial quotient, so then I'm doing this 1,000 times 5 is 5,000 because we put 1,000 in each group, and I'm subtracting. Now, so far, if you get rid of my 6 and 1 here, my answer looks the same as yours. But why do we bring down that 2? And that, or this 2 here? It's really a subtraction problem, and we brought it down because in our partial quotients method, it's a 0. So it's subtracting 2 minus 0 to get that 2. But in the standard algorithm, students aren't shown that's what that really means. So now, here you're looking at the 32, and I'm looking at 3,200 or 3,200 because I know that I can't take another 1,000 and put each group, so I'm going to look at the hundreds now. So here's my 32, and here's the standard 32. So 5 goes into 32 6 times, but this isn't a 32. This is 3,200. So when I put my 30 in there, it's really a 3,000, and that's a 600. So again, here's your 6 having a value of 600, and here's my 6 with a value of 600. But in this problem, the partial quotient, students can actually see what it is they're subtracting and what the values of these numbers are. And so I'm left with 261, and again, you have 26 here. So if I get rid of that 1, we have the same thing. But this 26 doesn't show you that it really has a value of 260, where in partial quotients method, it does show students that that 26 isn't a 26, it's 260. So I am focusing on that 26 because I don't have enough hundreds to put 1 in each group. So I'm looking at how many 10s. So this is 26 10s. And I know 5 can go into 26 5 times, or if I put 5 10s in each group, that has a value of 50. And I'm left with 11. You also have 11 on the standard algorithm side. And so that last step is the same because we're in the ones now. And if I take 11 ones, put it into 5 groups, I will have 2 in each group, and 2 times 5 is 10. And I subtract and have a remainder of 1. The partial quotients method is so similar to the standard algorithm that this shows students the values of the same numbers. So we got the same answer in the same number of steps, but the partial quotients does allow students to be more flexible in their thinking. For example, when they get a problem such as 8,261 and they want to divide it by 42, most students don't know that they're facts for 42. But what I do know, instead of coming off to the side and having to do all my multiplication facts for 42, I know my powers of 10, so I know that it's going to go in one time here because, so it will go one time, so that's 42, and it's 100. So I'm able to be more flexible with my thinking because I don't have to exactly find out what it is. And I don't know, I might not be able to say, well, it goes in 1,000 times, but I might be able to say, well, I know it can go in 20 times to get me 840. And students can repeatedly subtract, even if they don't know these facts, and still make headway on their problem by pulling out values over here. When they get with bigger numbers, it's easier. This also is better for students who struggle with math to begin with because it allows for them to make mistakes but continue to work through the problem without having to start over. And when I say mistakes, I don't mean that they're wrong in their mistakes, but if they only took out 500 here, they would then need to pull out another 100 and their answer would still add up to be the same. So the partial quotients method allows for them to think flexibly where the standard algorithm doesn't. And if students don't have an understanding of what's going on, their answers don't ever make sense to them and they're not sure when they've made a mistake because these numbers down here have no value. So I hope this helps clarify the difference between the standard algorithm and the partial quotients and that you can see really they are the same and they're showing students the same process. By having students do partial quotients first, it makes switching over to the standard algorithm much easier and more understandable for them.